Today, we'll be looking at probably one of the most interesting stories in science in some respects. And to really appreciate it, namely what we'll ultimately get through is the Stern-Gerlach experiment and its implications. We need to review a little bit of some of the basic concepts involved with it that deal with the interaction of magnetic dipole, sometimes or magnetic dipole moments, and define those and how they interact with the magnetic field. And to do that, the story really starts back in the 1830s with Hans Ørsted. He was a Dutch physicist that found that electric currents, here I've got a straight line electric current, a very long wire carrying a current I. And what one finds is it creates a magnetic field that kind of swirls about it in this fashion. In fact, if I get up here and look down into the wire, now the current is coming right out of the page at me if I'm looking down from this end. And the current I is coming out, and I'll indicate that with a circle with a dot here. That's the wire, and the point is the pointy arrow of the direction the current's going. Then the magnetic field circles about the wire, and in this fashion. It has magnitude that falls off as 1 over r. It depends on the current and a constant here that's characteristic of the magnetic field in a vacuum. And so the further you get away from the wire, the magnetic field gets weaker as R increases. And essentially, Ørsted discovered this relationship that magnetic fields are created by moving charges, i.e., currents, and that formed the basis of what we would now call electromagnetism or electromagnets. In fact, any closed circuit, really any current that you can produce, is in a closed circuit loop. And here I've got one that I'm going to say is circular, uh, and I'm not showing any batteries or anything in it that's causing the current. They would have to be here. But if I have this current flowing in this fashion about uh, in a closed loop in a circle of radius r, then in many respects that creates an electromagnet that is very, very similar to, or behaves very similar to, a small bar magnet. And if you remember a bar magnet, there's the north and south poles of a regular permanent bar magnet. Uh, the has a magnetic field. There's some magnetic field lines. Magnetic field lines, by our convention that we use, go from the north pole and then they end on south poles. And then one defines with this the magnetic dipole moment of this small magnet as a vector. It's a vector quantity because the field around it depends on the orientation, and so we know that to characterize that magnet completely, I have to give not only its strength but also how it's oriented to calculate the magnetic field. And this mu vector here has nothing to do with reduced mass or anything like that, but is a purely electrical or electromagnetic phenomena called the magnetic dipole moment, or oftentimes just the magnetic moment. It's bar magnets are magnetic dipoles. They have a north and a south end. The magnitude of this vector is a measure of how strong the magnet and then of course the direction it points is such that it gives you the orientation of the magnet. So you can completely characterize a bar magnet in that fashion. Now for current loops, we have something similar. I'm looking at this loop up here with the current coming around in it. Now I'm going to look at it edge on, and so this is the plane of that loop. It's current on this side. If I'm looking over here, it's coming out of the page at me, and on this side over here, it's going away from me. And this is the radius of this from one side to the other is two radii, and I've got the current I going through it. And for these, one can treat the magnetic field that's produced. It's a current, so it produces a magnetic field, and that magnetic field uh, can the magnetic field can be mapped. It looks very, very similar to the magnetic field of a bar magnet. In fact, here I've drawn some of the field lines for it. It has a magnetic field vector, a magnetic moment vector, I should say, pointing in the center here. That magnetic moment vector, we can develop equations for it. I won't do it. I'll just state them. But you can look at this, and the pattern here is very, very similar to, in fact, virtually identical for a very, very small current loop. Mu, the mu vector is directed in this fashion. The orientation of it is such that if you get in the plane of the loop with the current on one side coming at you and the current on the other side going away, that the magnetic moment vector points up. And pretty obviously, one of the things that makes a stronger electromagnet is the amount of current that's flowing in it. So you expect the more current, the stronger the electromagnet. And one that may be a little more surprising, it also depends on the total area that's enclosed by the circuit loop in this case. And for our circular element, then the magnitude of this magnetic dipole moment vector is the current that's flowing in it times the area enclosed. And in our case, we've got a radius r, and so the area enclosed is just the area of a circle of radius r, which is the pi r squared. So, and that then with the direction as I've defined, and also this magnitude totally defines a magnetic moment vector, and it's often referred to as just the magnetic moment, or if you want to be technically correct, it's really the magnetic dipole moment. Well, for a magnetic dipole in an external magnetic field, one obtained probably in some of your lower level classes, uh, the formula for the potential energy of the magnetic dipole of mu in this external magnetic field. It's related, it's a potential energy, and it's related to this scalar product, or the dot product, with a negative sign out front. If you look at this, the dot product, if you remember, is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two. Or another way you could write the dot product, if you know the xyz components of both of these vectors, you can just take their dot product as this sum. Multiply the x component of the two vectors and add it to the y component of the two vectors and add it to the z component multiplied to the two vectors. Here's a general orientation. Here's the magnetic dipole vector, mu vector. Here I've got a uniform magnetic field going upward, and then the angle it makes, this mu vector makes with B, is theta, and that's the one that's over here. The net effect of this is nature always likes to go to its lowest possible energy state. And if you look at this, particularly in terms of theta, the smallest it ever gets is when the cosine of theta is the largest. Right? So when cosine of theta, the largest it gets, is 1, then the lowest possible energy for this configuration of a dipole in an external magnetic field is just mu times b, tells the cosine of 0, basically, when they're totally aligned, is 1. The highest level is when the theta is equal to 180 degrees, and that would be the opposite. But the net effect is that these magnetic dipoles in external fields very rapidly, if they're free to rotate, will very rapidly rotate around until they align themselves with the external magnetic field. Usually, one lets the magnetic field define that direction, define the z direction, and if that's the case, then the magnetic field vector is just bz in the z direction, and bx, by, and bz, or bx and by are zero. So one lets the magnetic field, uh, and then the previous equation. Now in the second form, bx is 0, by is 0, so this reduces to a negative sign, mu z, the z component of the magnetic dipole of moment, and the z component of the magnetic field. And another useful expression is we know that the force on a magnetic dipole is just minus the gradient of its potential energy function. And here we get a negative sign in this relationship, and then we plug in the minus mu z bz here, and the two minus signs go away, and we find that in this particular configuration there's a force in the z direction. It's just the z components times the derivative of the magnetic field with z. And one of the things that implies for us is that if B is uniform, then B is a constant. In particular, BZ is a constant in a uniform field, and this derivative vanishes. So, in general, there is no force in uniform fields. In order to have a force on a magnetic dipole, you must have a non-uniform magnetic field, or in our case, since we've only got one component, what that means is that component has to be some function of z. It has to vary with where you are. Well, that's a quick overview, and just to recall some things maybe from previous classes that you had, maybe a physics course back a ways ago. And we'll continue with this next time.